Okay, so today we will be discussing how to check the convex and whether a function is convex concave, and we'll be trying one of those problem itself. We'll be checking which point is the optimum using univariate steepest descent, and uh, probably I will upload for the Newton-Raphson, how to use Newton-Raphson in a multivariate, because I think what sir showed in the slide, it is not, it cannot be used straightforward for multivariable. So yeah, I will be uploading a separate video for that. But for today's session, we'll be solving in Excel again, and I'll be showing you guys, like we'll be drawing the graphs also. So x1, x2. So trying to show you that this is how univariate will go, like a stepwise it will go to the optimum, and this is how steepest gradient it will go a little faster. Newton Raphson probably I will upload in another video, so it will be a little bit difficult. So yeah. Okay, so let's start then. So I have since already discussed what is a convex and concave function in previous video. We'll just go on ahead and we'll start with examples itself. So I would encourage you guys again to try to give me some of the answers. It will be simple only. So yeah, it will be helpful if you also participate. So we have a function 20 plus 2x minus x square plus 6y minus 3y square by 2. Now I want to know whether this function is a convex or concave. So the steps are, we'll first find the stationary point, and then we go on ahead and check the Hessian matrix is positive definite, then it is strictly convex. Positive definite, strictly convex. Positive not semi-definite, then convex, then negative definite, then strictly concave, and negative semi-definite, then concave. So that's the rule. Let's try to solve this now. Okay, so what do you think will be the stationary point for this function? Probably okay, so I have made a mistake here. So we just differentiated partial differential with x and with y. Here again I mistake. Okay, now you should be able to tell me, right? What will be the stationary point? Anyone?
Minus 1 and minus sorry 1 and 1 half.
One and little
Half.
bit carefully. Look at it a little bit more carefully. I think
2.
that yeah, correct. Yeah.
Hmm.
Probably just a silly mistake, but one and two, x y 1 2 is the stationary point for this function. So this is clearly visible, right? Should I zoom in a little bit more?
Yes, it is visible.
Okay. So 1 and 2 is the stationary point. Now we go ahead and make the Hessian matrix. So we just then differentiate with respect to x. So minus 2. So we have minus 2 here, and then we differentiate with respect to y. This function we get 0. So this is 0. Most of the time, Hessian matrix is uh, symmetric only. So we don't need to calculate, but there are some exceptions that are actually out of the scope of the syllabus itself, where the Hessian matrix will not be symmetric. So yeah, so for our case, we just need to calculate either differentiate this with respect to y or differentiate this with respect to x. We will get that non-diagonal value. Okay, so and then with this one with respect to y, dou to f by dou y square is minus 3. So can you guys, without calculating, tell me the eigenvalue of this matrix, Hessian matrix? Just by looking at it, we can tell the eigenvalue. Just take a guess. Okay, so maybe before that, tell me how many eigenvalues will be there. Okay, so no need to be worried if we are going to give wrong answers, because as I said, I have also made mistakes in this session also, and I have fixed them. Yeah, see, again this one is here. Probably some of you may get confused when you are looking at the PPT or watching the recording. So no need to be afraid of mistakes. So okay, let me tell this thing. The properties. Let me repeat the properties of eigenvalues. So eigenvalues for a square matrix, the sum of the diagonal elements is the sum of the eigenvalues. The determinant of the matrix is the multiplication of the eigenvalues, right? And then our classic method, we have the determinant of a minus lambda I is 0, then the lambda will be eigenvalues. But there is a trick for some type of matrices that are triangular matrices. So, are you familiar with what are triangular matrices? So you might have heard about this upper triangular matrix and lower triangular matrix, right? So can you tell me what specifically that means, upper triangular and lower triangular? See, if you don't say, then I will assume that you don't know. So if you know, you better say, so that other people also can understand. So the question was, uh, what are what do we mean when we say our matrix is upper triangular matrix or it's a lower triangular matrix?
All the elements in the upper above the diagonal is having values, others are all zero.
Correct. Yeah. So when we say a matrix is upper triangular, that means the below the diagonal elements, all the elements are zero. And when we say a matrix is lower triangular, that means above the diagonal elements, all the elements are zero. So, and a special case of these triangular matrices is a diagonal matrix, in which only the diagonal elements are non-zero and other elements are zero. Now, this is the property that one should know, that eigenvalues of a triangular matrix and diagonal matrix, which is a special case of triangular matrix, are the diagonal entries themselves. So, for this particular matrix, the eigenvalues will be -2 and -3 themselves. Okay, so both the eigenvalues now we have found it is negative. So can you tell me what is the nature? This matrix is positive definite or negative definite? Two options. Option A, it is negative definite. Option B, positive definite.
Positive.
Manu, you are saying it is positive definite. You can probably figure out the answer by my tone, right? So when, as I said earlier in previous videos, when all the eigenvalues are negative, then that particular matrix is negative definite. and when all the eigenvalues are positive, then the matrix is positive definite. When the eigenvalues are non-negative, that means the eigenvalues are positive and maybe zero, then it is called positive semi-definite. And in that case, our function becomes convex, and it has a global minima. For our case, this particular, we have a negative definite matrix. So our particular function, that is this one, is going to be a concave function. Is that clear, Manohar? Do you think
Yes,
I'm
sir.
making mistake, or do you recall now? I can make mistakes also. I'm not saying I will not make mistakes. Okay, so Manohar has said yes. So let's move forward with the next question. So in this question, you will tell me what is the eigenvalue. It's only a 2 by 2 matrix, so I expect that maybe in 1 or 2 minutes you can tell me what are the eigenvalues for this particular function. So again, the steps are same. First, we find out the stationary point. So I will go ahead and show you what is the stationary point and Hessian matrix, and I what I want from you guys is the eigenvalue. So yeah, I will do half the work. So when we differentiate this partial differential with x, so 2x plus y, and partial differential with y is 2y plus x. Then the stationary point is 0, 0, and then we make the Hessian matrix. We get a symmetric matrix 2, 2, 1, 1. Now, what I want from you guys is the eigenvalue of this particular matrix. You can use a software, you can use something, but yeah, you can solve by hand. But I would like to get the eigenvalue from you guys. So, is anyone solving, or I'm just waiting? Okay, so I am not sure if you guys are solving or not. So, if someone is solving, can you raise your hand? Okay, so no one is solving. Is it? I think it is too simple, so you are not interested to solve this. It would have been nice if we had solved, but no problem. I'll show the eigenvalues. So the eigenvalues for this particular matrix is 1 and 3. Both are positive, so it will be a strictly convex function. That means it will have a minimum. Okay. Now let's go to the main problems. That is, we'll use this same function, and we'll try to solve it. In this particular lecture, I will solve it using univariate and steepest descent. Step by step we'll solve it, so that you can get a feel for it, how to solve this particular question. So probably now you can, if you are not noting down earlier, I understand, because that is a trivial topic. So, but I would suggest that you bring out your copies or Excel sheet, whatever you are comfortable in, and you note down the steps that I'm going to use. Okay, so shall we start? Is everyone ready?
Yes, sir.
Okay, so we have function x square plus y square plus xy plus 10, and we want to get the point of optima using the univariate and steepest descent method. So let's just, oh yeah, let me zoom in. I remember. Is this much zoom fine?
Yes, sir.
Let me merge this and like fx plus, plus. This is our function that we are going to. So let me just name it again. Univariate. Oh, I have it name already. So univariate 1. Okay, so x naught and y naught. So I'm going to take 1 and 1, and same values will take initial guess 1 and 1 in the steepest descent also. So we have chosen 1 and 1. So let's try to optimize this function, or let's try to move along x first. So in that case, what will we have? We will have the d, the direction vector will be a unit vector along x. So it will be 1 and 0.
0.
Yes, correct. And we'll so basically x1 and x sorry y1 will be x naught plus 1 into alpha. So let me write alpha as a, and y1 will be y naught plus 0 into alpha. So let's just keep it as y, keep it at y naught. So then when we put these new values of x1 and y1, so basically it will be, let me write here 1 plus a and 1. So when we put these two values of x1 and y1 into our this expression, it becomes a univariate expression, and we will call it, let's say we call it as f of a. Merge it. Yeah, f of a. So it will be okay. 1 minus a whole square plus 1 plus 1 minus a, sorry, plus 10. So can you guys simplify this for me and tell me what will be the expression? So that you guys don't sleep, I am asking you to do this. Otherwise, it will be very monotonous. We'll write a simplified version here. Okay, so no one is interested in telling me the simplified version.
A square minus 3a plus 13.
A square minus 3a plus 13. Okay, it seems to be correct. Yeah, it is correct. So now we will use this to get the optimum value of a, so that our fa is minima. So what do you guys suggest? Should we use Newton-Raphson, or should we just do the differential and get the value of a?
If we differentiate and equate to 0.
Yeah, so we can. Yeah, that's what I am asking. So do you want to go
Yeah,
with?
yeah.
Okay. Okay. So then we have our f. dash a, and it is just why I am writing this. We will understand in a little bit. 2a minus 3. So our a value for this particular moving along x direction is going to be 1.5. Okay, is that correct? Maybe we did some mistake, huh? Yeah, okay. A value is 1.5. Oh yeah. Okay. See, I did one mistake here. No one noticed. So I changed it to 1 plus a, right? So it should have been 1 plus a square and plus 1 plus 1 plus 1 plus a square. Okay, so that's my mistake. I apologize for that. So what will be the new expression now? It will be a square plus 3a plus 13, right? Nothing else will change, no?
Yes, yes.
Okay. We have a 2a plus 3, and the value of a will be minus 1.5. Okay. So now we have x1 and y1 as 1 minus 1.5 will be minus 0.5, and this is 1. Now what we do is we move along y, and in that case the direction vector d is going to be 0, yes, and 1, and our x, so let me call it at x2 and y2. So and x2 and y2, so it will be minus 0.5, x will not change, and y will be 1 plus a. Now we put these values into this particular function, and we again get our fa. So probably it will be, yeah, I think you should do this because it will be a little bit, it will be a kind of a refresher or a warm up for you guys when you are doing it in exam. So yeah, if you want to go ahead and do this while I'm writing this, it will be very nice. So this is our expression, and we have to simplify this so that we can differentiate it easily and get the value. Or maybe you can tell me directly what is the value of a for this to be minimum. You want to give it a shot? Okay.
Is it 0.75? A
Yes.
is equal to
Correct. Correct. So point a is equal to 0.75. So let me write here the simplified form. Okay. Maybe Manohar can tell us what is the f dash a directly. What was the f dash a, Manohar?
f dash a is 2a minus 1.5.
Seems to be correct. So we'll use this, and we got a is equal to okay, Manohar, are you sure this is plus? Oh, sorry, minus. So maybe let me also do it.
No, sir. It is plus 1.5.
Plus 1.5.
Yes, plus 1.5. And it
Okay.
is coming minus 0.75.
Yes. So we have our a value is minus 0.75. Yeah, this seems to be correct. So yeah, we'll go ahead with this value, and we have x2 and y2 again. X will not change because we moved along y, so it will be minus 0.5. Oh, sorry. And y will be 1 minus 0.75, so it will be 0.25. This is our x2 and y2. Now again we will move along x. We have a new values. We will have, sorry, I should write here. So we will have our new values will be minus, so maybe I should write d also, right? So d again, when we are moving along, x will be a unit vector that will be 1 in x direction, so 1 0, and x3 will be minus 0.5 plus a for the alpha. So we want to say, okay, don't let me do that, so let me write a minus 0.5, and it will be 0.25. So f of a, and yeah, we have to again put this particular value into this function and get a univariate function in fa. So yeah, you can also go ahead and try. I will try on my side. So I am using a software, MATLAB, to simplify this particular expression for me, but you won't be able to use that in exam. So maybe if you want to give it a shot, like Manohar, you can try. Okay, so I don't think MATLAB helped me a lot, but this is what I am getting. If this is what you are also getting, then it is correct. The major problem will be with coefficients only, so the constants only. So yeah, you can check the constants after you have simplified this. So what do you say, Manohar? Is it looks correct? Does this look correct? So by the time you are doing that, maybe I will do the differential. Did you get this, Manohar?
We got 2a minus 0.75 differentiation.
Correct. Very good. That's what we will get. So we'll have our a value as plus, we can just leave it at that, plus 325, right? Sorry, 375, it seems. Yeah. We have our a value as 375. So our x3 and y3 will be is equal to minus 0.5 plus 0.375, that is minus 1.25, and 0.25. So y will remain the same. So we have, so actually we can plot now itself and see that it is going to the value of, since you already saw in our, when we were doing this particular function, we were checking the optima for this particular function using our calculus. we saw that it was 0 0. So we can see that this particular problem is slowly approaching to near zero value. So we'll do probably two more, and then I will plot it so we can see much more clearly how this works. So we have our now we have moved along x. So that's the thing. So we have made since we are using here normal calculus, we don't have to check for f dash a is equal to for that particular value of a whether it is 0 or not, because we are getting the a by making this 0. But what sir suggested in class was we use either golden ratio or Newton-Raphson. So I will share this particular Excel sheet where I have used this golden Newton-Raphson technique, and you can see that f dash a becomes 0 for these particular values of a that we are getting. Yeah. So yeah, but in the exam, I think for the safety of time, will you can also use this particular thing itself. One more thing I would like to say that these methods are becoming less and less popular as new computation tools are coming along. So that's why I think in your assignments also you don't have probably much problems to solve these this kind of multivariable optimizations using univariate and steepest descent, right? Do you have any question is in assignment, Manohar, where they have specified to use this kind of methods?
No, sir. I haven't yet seen that.
Oh,
I'll have to go through that.
okay. So yeah, probably they are not there. You can check. So yeah, so we have now our y3 and x3 and y3. So when we again move along y, we will not disturb the x. So the x is as it is. We have to disturb our I, however. So we'll be direction vector along y direction, and we add the length of a to that particular vector. So we get 0.25 plus a. Now again, it's a tedious process. We'll just put this into this particular expression. We'll simplify. Probably, don't think we need to simplify this. So this time I will not simplify, and we can directly check what is the, the value of a for this to be 0, for the f dash to be 0. But I should write this so that when someone is looking at it later on, they have something to follow. So probably this will be okay. Maybe I need to extend this. Yeah, so this will be the function, and the differential. So if I don't differentiate it, we will have 2 this, and yeah. So let me just do this, and meanwhile, if Manohar, you solve it, you can tell me the value of a, and we'll cross verify if we get the same value. So yeah, I am getting something like this. Tell me, Manohar, if you are getting something different. So are you also getting this, Manohar?
sir. Yet solving.
Oh, okay, okay. Yeah, yeah. You take your time. Take your time. So I'll just write the value here. You can cross verify what you are getting.
Yes, sir.
Okay,
2a plus 0.375.
you're getting plus 0.375, huh?
Ah,
Or 2a plus, okay, okay.
2a plus 0.375.
Yeah, yeah, exactly. So yeah, that will be this one. Yes, correct. So then when we put this value in our x4 and y4, we simply get is equal to plus 0.00625. Yeah, so it's pretty close to the y has come pretty close to x. Just let's just do one more for x, and then I think we will have a pretty close value of x also. So we have x5 and y5. So now again we move into in x direction. So 1 and 0. So x5 and y5 will be written as y we will leave as it is. So we will not disturb the y. So we have to write x, so it will minus 0.125 plus a, and so we'll write a minus 125. Yeah, and yeah, we put this again into our expression and simplify this. Be pretty complex, I think, to simplify this, but we don't actually need to do that because we are not using the function value, or we are not following the classical step by step approach. We are directly calculating the f dash a. So let's see what is the f dash a for this particular problem. So what I think you can also use, Manohar, I don't know if you are using this or not. You can see that these things are constant. So while differentiating, you can just leave these, and we can differentiate this and put this and this summation of this equal to 0, and we can get the value. Okay. So what I mean by that is we will see that here when we differentiate this term, it will be 2 into a minus 0.125. We leave this term, and then here this term is a constant and this term is constant. So we don't need to multiply and simplify this. The differentiation of this will be just plus 0.0625. So basically the expression we need to simplify is solve is 2 into a minus 0.125 plus 0.00625. Yeah, so yes, you can use this also to easily solve the problem.
2a plus 0.375.
You are getting 2a plus 0.375. It is a pretty big value, no? Can you check again? So here's one more trick which you can use, Manohar. So here, look at this particular thing. So we actually if we know what is the answer somehow, and we are approaching towards answer or not, we can see. So this a minus 1 to 5, it has to go near 0, right? And to go for this to be going near 0, we need to reduce this minus 1 to 5, 1 to 5, so the a should be positive. So if you are getting something 2a plus something, that means that the a that you will get after solving will be negative. So you can, you can kind of have a cross check. So probably you should get something like this.
Okay, sir. 2a minus 0.2438.
So what will be the value of a then?
It is 0.1219.
Okay, are you sure?
Sir. 0.1219.
Okay, yeah. So we got this. Uh, so yeah, I think then it should be 2a minus point 0.2 something, no? Yeah. So it will be 2a minus point 0.2 something, not 2 point something. So maybe some calculation mistake.
2a minus 0.2438, I say.
Yes. Yeah. Exactly. Exactly. Yes.
Mhm.
Yeah. So we also have our value. So it will be minus 0.125 plus this, and y we will leave as it is. And yeah, now we have pretty close values to 0, so let's just plot it and see how actually we got what was the variation of this thing. So rather than plotting, I will, okay, let me plot here itself. These values are okay. Yeah, let me use values from here. So this is the same I had solved earlier, so I will use that. We are also getting same values. Or maybe I did a mistake here earlier. So now it is coming like this. Okay, now we will plot these particular values in a plot and see that how nicely it has gone step by step. And one more interesting thing I will tell you that is that, yeah. So you can see that we started from 1 1, and then we moved to minus 0.51, and it's how it is like going from step, and it is coming close to the 0. So if you uh, do some more iterations, it will have so a little bit more steps, and eventually it is going to come near to 0. Yeah. So this is something I wanted to show. And one interesting thing about this is, you see this particular line, right? So can you tell me the length of this line? Do you know any number that we have calculated that represents the length of these lines?
It is 1.5.
Yes. So do you know any number that we calculated in the first iteration that was 1.5? Okay, so let me tell you. Let me show you. So here I was saying, so we will choose a direction vector, we will move in x direction, and it is a unit vector. So this alpha that we calculated, that is actually deciding whether it is plus x direction or minus x direction. So when it is minus 1.5, yeah, tell me one.
Yes, yes, yes.
So
So that alpha is in the negative direction of the magnitude 1.5.
yes. So in the first one we moved minus 1.5 in x, and the second one we
Correct.
moved down by
Yeah.
0.75. Yeah. So this is what this actually signifies. So someone
Yes.
can, yeah, someone can ask in the exam, like to make it tricky, unnecessarily tricky, that what is the length through which your first step moved or something like that. So now you can answer that. Yeah.
Yes.
Now
It just shows the amount we are moving in the given direction, X or Y.
yes, exactly. Yeah. So now we will quickly. So one good thing about this. Now we'll go for the steepest gradient. So one good thing about the steepest gradient is it is not going to take that many iterations. We will be able to just solve in 3 iterations. So let's finish that quickly. And I will probably upload the video for the Newton-Raphson, because there are some complications that I have to discuss with professor. Like, so yeah, steepest gradient. Let me name it as one. Okay, so what do you suggest? So we will take these values as same. Yeah. So and yeah. So tell me, Manohar, what is the direction vector that Sir chose for this steepest gradient?
It is the first derivative we chose.
Yes, correct. So we have 1 1. So I don't think I should have written it like this. Maybe I will write here f dash of x. So it is just the partial derivative that we have already calculated. So with respect to x, it will be 2x plus y.
2x
Ye-
plus y.
Yes, correct. And with respect to y,
2y plus x.
yes. Now we put the value of x naught and y naught in this particular equation, and we get the value as. So I am writing this so that I drag this down, don't have any. I don't have to do again and again. So this is, we are having 3. So what we can do is we can actually the direction will be minus of f dash x, as Manohar has suggested. But what? Okay, let me do this. So let me just not write this. So it will be minus 3 and minus 3, right?
Yes, sir.
But what else we can do? Minus 3, if I put here, it will be a very big numbers, no? So what else we can do with this? Can we, since we only needed the direction, can we make this something else instead of 3 3? So okay, actually we can. So 3 3 basically is giving us the direction. So let me just open thing to make it more clear. So basically you have now decided, okay, that your vector is going to go along this line. So where this is 3 and 3, but we use this particular value for direction only. So we have identified the direction is here. So we can
Yeah. Make it 1 1 also.
yes, so we can make it 1 1, that preserves the direction, and we don't have to do unnecessary some more big calculations. So when we have this 1 1 and we want to get the negative of f dash, so we'll make it as direction as minus 1 1, and our x1 and y1 will be written as, so we have now the direction. Now we will get the length. So 1 minus 1 into a, and 1 minus 1 into a. Is this one clear? It is clear.
Sir, how that x1
Yeah, so okay. So
x1
x1 was nothing but x1 is equal to x naught plus alpha into d, right? So it was so let's say it is x1 and y1, and this was our 1 and 1, and we have decided the direction in which along which this is going to move. Now we just need to know what is the magnitude of the direction. Along that direction we need to move, so we need this a also, right?
okay, okay. 1 minus a, 1 minus a.
Okay, so we have this, and now we will put this particular uh, 1 minus a 1 minus a into this expression, and it nicely conforms into a very simple looking expression that if you look at it, that's why I chose also a symmetric equation. So is this correct?
Yes, sir. 3a square minus 6a plus 13.
3a square minus 6a plus 13. Yes, correct. So when you simplify this, you will get that. And now we will go for the differentiation. So what will be the value of a for this?
It is 1.
Okay. So we will have something let's say 6 and 1, sorry, 6 into 1 minus a square, or minus 1 plus 1, it doesn't matter when we are putting it to 0. So a value we got as 1. So now when we, yeah, see, so in one iteration itself, I think we have gotten the value, right? So our x1 and y1 will be 1 minus a, that is 1. So 0 and 0. So this is the power of when you are using differentiation to go into the right track. So let me just make it as center. So okay. So is this one clear, Manohar?
Yes, sir.
Yeah.
Yes, sir. Yes.
So yeah. So you, if you look at it, if we were to choose 3 3, I think that's what I did in this particular uh, something else I had done. Yeah, I did some mistake here. So eventually, yeah. So maybe I'll share this one when I'm sharing the Excel. So in this particular thing, just by one step itself, we have gotten the value of our optima point. Yeah. So that's good. Okay, so yeah, so I have tried something with the Newton-Raphson also, but since the in the class, what sir showed was this expression, right? Can you see this expression?
Yes, sir.
Yeah,
Yes.
so you cannot actually use this expression to solve for the multi-dimensional. So I will have to. So we actually have to use Hessian metrics and all those things for getting the optima using the Newton-Raphson. So I'll be sharing a separate video for that in the YouTube or what. So have you gone through the next week's topic?
No, sir. I just completed this week's week 4.
Oh, okay, okay. So I will see whether if that week's topic is something that I have already discussed in the previous class. I will be discussing the Newton-Raphson method in more detail for multivariate in the next class. Or if there is something new, I will upload a separate video, and you can find that in the YouTube channel or the playlist that I have uploaded. So yeah, I think for today we have covered sufficient. So I think you should be able to solve the assignments, and probably these kind of problems are not in assignment, but something that clears the concept a little bit better. Okay, yeah. So thanks, Manohar, for participating in today's session. Active
Thank you.
participation. Yeah. So
Thank you, sir. Thank you.
I will end the session today then. Thanks.